Okay, let's go ahead and get started. Welcome to class. This is January the 23rd and week 3. We're going to talk about some of the cool stuff in chapter 5, so hopefully you've already had a chance to watch all the videos and are up to speed on probability. We will do lots of interactive, what I hope you guys will find is fun stuff. But let me first of all just say, did you guys know that the Eagles are going to the Super Bowl? Huh? Oh, you knew that already. It's awesome, yeah? There's at least a few fans wearing paraphernalia. Okay, so before we jump into this chapter 5 stuff, are there questions about homework 2 that I can help you with? Show you how to do any of those questions? No, everybody's good on homework 2. Have you guys looked at homework 2 yet? It's not due till Thursday, so maybe not. Well, yeah.
How do you figure out cumulative frequency?
Cumulative frequency, are you referring to problem number 14?
No, I think it was like 3.
Okay, well, let's look at that then. Homework 2. My pen doesn't seem to be working right now, which is not good. Okay, so let's go to assignments. Homework 2. Actually, let me. Okay, so you said number 3. Okay, so it's this cumulative frequency that you're worried about. So we've got batting averages for the New York Yankees, and we want to come up with a frequency chart or frequency distribution, and with the midpoint, the width, the frequency, the percentage, relative frequency, and then cumulative frequency, and then I'm not sure why it says %, but let's look at the Excel file. And so here's the raw data, and we want to know which of, or how many do we have between 0.2 and 0.25. All right, so here the data is listed just kind of, I guess it's alphabetically by first name. Is that right? And the reason I looked at the data file is because I can see, I guess I see that same thing here. Okay, so this one is listed numerically. All right, so I can make that a little bit bigger. And the question says for the values between 0.2 and 0.25, is it?
Yeah.
So 0.2 and 0.25, and usually 0.2 is going to be included in that, 0.25 is not going to be included. So we want to come through here and say how many are in between. So here's our what are we calling them? So we've got the midpoint, the width, the frequency, and the percentage. So let's come over here and say here is the midpoint, the width, frequency, and percent. Right, so we can do this for all of the categories, or rather all of the bins, although the question's only asking for 0.2 to 0.25. So I'm just going to fill in that one. So the midpoint between 0.2 and 0.25 is 0.225, right? The width, 0.05. And then the frequency, how do I get the frequency? The frequency says how many do I have in this within 0.2 to 0.25. So all I have to do is come over here and count. Where does it start? Here's the first, or the top one in that. I guess these are not in order. Okay, so I'm going to sort these things over here so that I get them in order, so this is easier to deal with. All right, so I'm going to come over here and I'm going to say sort. Data sort by average, and I'll do, I guess we'll do smallest to largest. Okay, so now that I've got it sorted, and of course you don't have to sort the data, you can just go through and look at it and manually try and find these things. But here's the first one, Bubba Crosby, and then we got Craig Wilson, and so forth. And we go all the way down to Nick Green. Now this guy here, Andy Cannizaro, he's not in that bin, because 0.25 is going to be the cutoff, and that's going to be included in the next bin up. So how many are here? We got 1, 2, 3, 4, 5, 6. We can come over here and say there's 6. Now the percentage, of course, is just going to be of the total number of players, and how many are there? We've got 4 down to 28, 24 players, I guess. So the percentage is just going to be equal to 6 divided by 24, except for that's not a percentage, is it? That's a proportion, so the percent is 25. And then finally they ask us, what's the cumulative frequency? So how do I find the cumulative frequency? What does that mean? That means I'm adding up, starting at the very bottom, and I'm going all the way up to and including this bin. Okay, so to get this cumulative frequency, I'm going to come over here and I'm going to say Andy Cannizaro is not in, but how many are? And it's going to be a total of the 6 that I already counted plus 1, 2, 3, 4. So it should be 10. So we get 10, and the percentage is just going to be 10 divided by 24 times 100. And so we'll just come over here and put these things in. Frequency is 6, frequency is 10, and then we'll check our work and just see if we got those right. And it looks like we did. So remember, cumulative is exactly what it sounds like. Just start at the bottom and start adding stuff up as you go. Okay. So my pen's not working for some reason. So I do actually want to look at number 14, because oftentimes I get questions about this one. So let's do that one real quickly. All right, so we have Kentucky Derby winning times, and it says here that we have 84 years worth of data, but there's only 69 observations. So I guess what they did is they randomly sampled from the 84 years, 69, and then they, instead of giving the actual data points, they gave a frequency distribution. So between 119 and 120, that's happened twice. Between 120 and 121, that's happened twice. Between 121 and 122, it's happened 20 times, and so forth. Okay, and now they want us to come in here and fill in this this chart so that we can get an estimate for the mean and the standard deviation. And I'm gonna see if I can get this thing to write on it. Okay, so I got to use my finger to write on it, but that will work, I guess. So this is it's kind of a pain in the neck, but so this is homework 2.14, and the first part of this question says, well, we want the average, the standard deviation, and the coefficient of variation, and to get those, since we don't have the raw data, we're going to use a method where we take, so for part A, we want x bar, which is just 1 over n times the summation of the xi's. Oh, what's going on with that? Let's see. There we go. So we want x bar, which is just 1 over n times the summation of the xi's. Now, we don't know what the xi's are in this case. So what are we going to do? We're going to estimate this. So we get 1 over n times the summation of the frequency times the midpoint. All right, so we'll come back over here. And sometimes you have to do this. So what this is saying is, if I just count how many observations I have in a bin and then multiply that by the midpoint, that's going to be an estimate for the summation of the values in that bin. So in other words, I come over here and I say I've got frequency of 2. What's the midpoint? The midpoint's going to be 119.5. So if I want to know what the total value is, or the total sum is for these two observations between 119 and 120, I can't know what it is, but I can estimate it by saying I've got 2 in that bin. Let's multiply 2 by the midpoint. So 119.5 multiplied by 2 is going to be my frequency times the midpoint, or the total sum of the x values in that range. Okay, so in order to get what I'm looking for, I just need this column f times m, and I'm going to look at the Excel spreadsheet again on this one. Let's get rid of that thing, and so you can see what's going on a little better. Too big. Okay, so let's just add in a midpoint. Now the midpoint is going to be equal to the average of 119 and 120. So I could very easily just use my calculator and say average 119, 120. That's going to give me 19.5. But the easier way to do this is to use the function average. So equals average, and then I'm going to put in 119 and 120. And I say okay, and I get the midpoint of 119.5. I'm just going to copy that all the way down, so I do that for all of these things. Okay, I've already got the frequency, so this is the F. So to get FM, I'm going to take the frequency times the midpoint. So 239 is what I need to put in over here. So here's 239. And then I can look on the table and see what else I have. The 126, so 253, go right here. Alright, and then the total, to get the sum of these things, that's going to give me what I need for the average. So I'm going to come down here and say, give me the total. So this is equal to the sum of all these values. And notice I'm not summing each individual data point. I don't have 69 things that I'm summing. Instead, I just have whatever that is, 8 or so. So I've got 8 bins, but each bin represents, so this bin right here, 2430, represents 20 observations. So those are all kind of clumped together. So I need the average, or X bar. And so this is just going to be equal to this number divided by the total, 69. So 122.93. I'll just copy that and throw it in here. And let's see, what else do we need? Then we'll check this in a minute and make sure we get it right. Come back over here. Now we want F times the quantity m minus x squared. So we'll call that part B. And what we're really trying to find is the sample standard deviation. And so this is going to be equal to the square root of the summation of xi minus x bar quantity squared divided by n minus 1. But again, we don't know what the x's are. We do know what x bar is, but we don't know what the x's are. So we're going to estimate that again with the summation of f times m minus x bar quantity squared divided by n minus 1. Now, I didn't write it in here, but the index on this sum goes from 1 to 69, but the index on this sum only goes from 1 to 8. So keep that in mind. These are not, we're not summing up 69 times in both of these. But nonetheless, I need to get this quantity f times m minus x bar, and they give us the formula right here. So we're going to come over here and we're going to say f times m minus x bar quantity squared. So how do I get this? This is going to be equal to f so f times the quantity m. What's m? It's the midpoint, minus x bar, which is 122.93, and then I'm going to square that. Okay, so that's going to give me that first value, 23.59. And what's going to happen if I copy this the rest of the way down? Is it going to give me what I want? No, why? Because I have relative references in this. So what do I need to do? $. Actually, I only need $1 but we'll just put both of them in. If I put it on the 16, before the 16, that ought to do it. Okay, Okay, so here's all of our values, and so now I want to take the sum of those. And that gives me the summation of f times m minus x bar squared. So that gives me this part right here. So I still need to take the square root of whatever that number was, 188.95 divided by 69 minus 1. That's a 6, not a 0. Okay, so to get the standard deviation, I'm going to take the square root of this number divided by the quantity 69 minus 1, and we get a square root of, or a standard deviation of 1.66 something. All right, now I'm gonna put one of these in here. I'm not gonna copy them all in. We'll just check our work and see how we did. Okay, so what's going on? I got the average right, and I got the standard deviation right, but I didn't get this right. What's the problem? The problem is I didn't read all the instructions. It says here, round your answers to 2 decimal places. And a lot of times you can get away without rounding at all, and I wish the Connect people would just put that as kind of the default, but sometimes they say round to 2 decimal places. So how do I do that in Excel? If I come over here and say I'm going to change this function, this equation, I'm just going to put round, the function round, whatever I'm rounding, comma, how many decimal places I want, 2, and then close that off. So it takes it to 23.6, and I'm just going to copy that all the way down. So now if I copy that and come over here and say, let's redo this part. There's 23.6. Now when I check my work, I still got it wrong. Why did I get it wrong still? So I rounded that one to 2 decimal places. What did I not round to 2 decimal places? I didn't round the mean to 2 decimal places. Even though it's telling me I got it right, I didn't round it to 2 decimal places. So I got to come back over here now and put the round function in. Round that thing, comma, 2 decimal places. And look, that changes it to 23.53. So now when I come back over here and I put it in one more time, I should get it right this time. And look at that, I did. Okay, so be careful. The reason I'm doing this problem in class without anyone asking me about it is because of that reason right there. So check the rounding, round at each step. You're probably doing it right, but not getting the rounding step done. I will put this Excel file on Blackboard. Yeah.
So the whole process is happening at m minus x bar squared is just going to get to the standard deviation.
Yep, because then we're going to sum all that up. Here, let's see, we're in the wrong place. But we're going to sum all of that up right here, and then divide by, here's the formula, divide by 68, which is n minus 1, and take the square root of that. And that will give me the sample standard deviation, or rather an estimate for the sample standard deviation. Okay, so if you run into trouble with this one, just make sure you double check the rounding. You're not always going to get this wrong if you don't round, but if you do put a number in that tells you it's wrong and you're pretty certain you did it right and you're getting these other things right, then go ahead and change that. Okay, so that's one of the problems that we have with Connect. But I will say that I have been working with the guy in Lebeau Intech, and we are going to be able to use Excel on the midterm exam. So make sure you learn how to do this stuff in Excel. There will be data, questions that say here's the data file. Use that as your calculator, and I'll show you some additional functions today that you can use that you want to get to learn how to use. Okay, so let's move on. We're going to talk about probability. And when you think about probability, and it's kind of become popular of late, what do you think about when you hear the word probability? What is probability? Okay, the chance. So you think of a number, right? Chance that. Okay, the likelihood of an event happening. So any other ideas? You've heard the term odds before, probably. Are odds and probability the same thing? So what are the odds of successfully navigating an asteroid field? Anybody remember that movie? Star Wars Episode 5. They haven't remade that one yet, but they probably will. They'll call it Episode 8. Oh wait, no, Episode 8 already came out. Anyway, odds and probability are not exactly the same thing. They're a little bit different, and I'll just mention that if you have odds of some event A, and they're written A to B, all right, so you're thinking about the Eagles and the Super Bowl. What are the odds for the Eagles in the Super Bowl? Anybody know? Are they favored?
No.
They're not favored. Okay, so if the odds of A happening, and usually in sporting events they give the odds against something happening. So if they said 5-1 for the the odds for the Eagles, usually they're saying the odds against the Eagles are 5-1, which means they're heavily unfavored. So if we had 5-1 here, what's the probability of A then? So odds means it actually is talking about the ratio of the probability of winning to the probability of losing. And so if you have the odds, you have the probability, but odds is not equal to probability. So in this case, the probability would be 5 divided by 5 plus 1, or it's A divided by A plus B. That's the probability. And again, this is odds of A, so whatever A is, you define that event and say the odds of that happening. That means the probability of it happening are A divided by A plus B. Again, in sports, they usually give the odds of against something happening. So you got to keep that straight. But probability is really the study of uncertainty. Right, and that's what you should think about whenever you hear about probability. So uncertainty, what does that mean? What is uncertainty? Okay, so there's some error involved with that, right? You've heard the term randomness before, probably. Right, so if something's random, that means that it's uncertain. And what does that mean? If you're uncertain about something. Is anybody uncertain about what's going to happen February 4th? When the Eagles play the Patriots? Okay, so you don't know the outcome of that. Nobody knows the outcome of that. There's some uncertainty involved with the outcome of the Super Bowl. And it doesn't really matter how much information you have about the teams, about the situation, the setting, the temperature, the alignment of the planets, everything that might possibly affect the outcome of that game. You can have all that information, but there's still going to be uncertainties on top of that. And so one of the key concepts for statistics is, how do we, first of all, I talked last time about extracting information. When we extract information, what do? We go through and we look at all the data that we have and we say, here's a signal, and the signal is telling us something about some event that's going to take place. And we can understand all that information, take that information into account, and we want to base our decisions on that. But that's not everything. In addition to the signal, there's always noise, there's always uncertainty, there's always randomness. And it's the random parts that we can't predict, or shouldn't even try to predict. Does that make sense? Okay, so so in this class, we're going to be trying to explain variation, explain as much of the variation as we can, but we always want to allow for there to be uncertainty. We want to understand the uncertainty, and you can think of uncertainty as variation as well, but it's the random part. So there's variation that comes from the process, and then we have variation that comes from things that you can't explain. From maybe it's a process, but you think of it as just random error or error. Okay, so let's see. Let me pull up. Okay, so has anybody ever gotten an email that says Apple stock next week is going to go up? Anybody ever gotten an email, something like that? Maybe not identical to that, but somebody's making a prediction about the future, and then and sure enough, you say, well, these guys think they know what they're talking about, so let's watch and see what Apple stock does next week. And what happens? Apple stock goes up. Okay, and then then you get another email from the same people that said, hey, last week we were right about Apple stock. You should have, it was going up, you should have bought low, you could sell it this week and make some money, but you might not want to sell yet because it's going up again next week. And so you say, okay, well, I'll just wait and see. And sure enough, next week it goes up again. And then you get another email back that says, hey, you might want to think about selling your Apple stock because it's going to go down next week. And you haven't bought any yet, but you play along and say, okay, I'll just see what's going on. And sure enough, the next week it goes down. And this happens over and over and over again for, say, 10 weeks. And finally, you get an email from these guys that says, hey, we were dead on every week for 10 weeks. Do you think we know what we're talking about? Do you think we know what we're doing? Stock picking? Well, if you do, if you want to, wake up to the real world and not chalk this up to random guesses, then why don't you consider investing your money with us, and we'll take care of you. So what do you guys think about that? Would you invest your money with these people? I mean, 10 weeks in a row, they got it right. That's like flipping a coin 10 times and saying it's going to be heads, heads, tails, tails, heads, tails, tails again, tails again, tails again, heads, and so forth. And they got it right every single time. That's pretty good, isn't it? That's pretty amazing. What are the chances that they could do that just by guessing? Talking about probability and numbers and randomness and so forth. If they were just to guess, you'd say there's a 1 out of 2 chance they get the first one right, and then a 1 out of 2 chance they get the second one right. So it's a 1 out of 4 that they get the first 2, and then 1 out of 8 that they would get the first 3. By the time they get to 10, what do we have? (1,024) different ways in which they would have had to guess just one. One of those is what actually happened, but there's about 1,000 ways to do that, to have a sequence of heads and tails or ups and downs. Okay, so chances that they just guessed randomly are 1 out of about 1,000. That's pretty small, isn't it? So should you trust these guys? And they're pretty good. Well, what is it they're doing here? What is it they're trying to make you believe that they can do?
Essentially that the accuracy of the how they were performing on their assumption that the button will stop the
Okay, so they're trying to make you think that if they're making the decisions for you, you're gonna make money, right? If it's going up, they're gonna buy and then hold and see what's gonna do the next week, check their magic ball or whatever it is they're coming with the forecast. It's going down, they're gonna short sell it, and you're gonna make money either way, right? And then they're gonna say, well, give us 2% management fee, and everyone will be happy. All right, so that's what they're saying on the kind of the surface. But what are they really saying? Okay, I like where you're headed with that. They know how to follow trends well, but how good are they at it? They're completely accurate, 100% track record. Okay, that's a problem. That's a flag. If you know anything about probability, then you look at the situation like this and you say, hold on, what these guys are really saying is we can predict randomness. Okay? And if anybody ever tries to tell you that they can predict randomness, what are they? They're liars. Okay? You can't predict randomness. Why not? Because randomness, by very definition, is that which can't be predicted. Okay? So there's too many variables going into the price of Apple stock or Microsoft or whatever it is next week that you know for a certainty what's going to happen. So how do they do this then? How do they get it right 10 times in a row?
I think there is a chance.
They can guess, yeah. There's a chance. It's very small. So what do they do?
They're probably like doing some research into the stock. Maybe Apple like 1 week released a new product, and then they thought like after 2 weeks it got overbought. So
Now that's what you would think a good money management firm would do, right? But they're not going to be perfect when they do it, and that's what they want you to think they're doing. But these guys are actually the lowest form of life known to man. The first week they sent out, guess how many emails saying Apple stock is going up? They sent out 1 million of them. But they also sent out 1 million emails saying Apple stock is going down. And then they said, okay, Apple stock goes up, down, we don't care. Whatever happens, Apple stock goes up, we're going to send another email to half of the 1 million that we sent the first email to. 500,000 get the second email that says Apple stock's going up, and the other half, the other 500,000, gets an email that says Apple stock's going down. And then I don't care what happens, it goes up, great. Well, now we got 500,000, and so we divide 2 million by 1,000 and 24, And how many people do we have now think we really know what we're doing? A couple thousand, right? So of those couple thousand, I can get a few that like the track record and say, oh yeah, here's my life savings. You guys do your thing with it. You can make some pretty good money. Move to the Cayman Islands, buy a yacht, buy whatever I want to buy with all that money, and they'll never hear from me again. Right? Because I'm not really in the business of picking stocks. I'm in the business of tricking people. Okay? So the study of uncertainty, if you understand that, will help you in situations like this. I asked you guys to do this ESP experiment. Did anybody get a chance to look at this? So who didn't get a chance to look at it? All right, so you should look at this. Well, I mean, I guess the gig's already up, but Clifford Pickover is actually a real person, and he's written 50 books and has 450 patents, and he's a really smart guy. And so he said, look, I'm going to do an experiment with ESP, what is that, extra sense, I don't know, so you can communicate with your mind, right? So he says, all right, come to this website, click on one of these things, and now here are 6 different cards, and what you need to do is pick one of those cards. It doesn't matter which one. Now he asked you to say it out loud, but I'm not going to ask you to say it out loud. Just in your head, pick one of these cards, just one of them. That's all you have to do is pick one and memorize it. Okay, and now you have to come down here and click one of these 6 eyes, and he's going to read your mind. He's going to remove your card. Okay, so everybody knows which card they've picked. He's just going to remove your card, okay? So how'd he do? Is your card gone? How'd he do that? Is it ESP? Is it ESP? This is the same argument these guys are making with Apple stock going up. This is sleight of hand. What did he really do? He changed all of the cards. Now, if you look at the comments, they're really funny. Let's see. I don't think you choose the card too quickly and don't give the computer sufficient time to randomly choose other cards. Also, the thought occurred to me that people tend to mouse click on the side of the screen where the chosen card is located. Okay, so there's all sorts of explanations as to what's going on, and probably Pickover wrote all these himself because they're really funny and none of them have the right explanation, but goes on and on and on and on, so you can check it out if you like. But when I first saw this, I thought it was pretty clever, because what does he do? He just switches, and you can go back and forth and see, here's the same cards we started with. I'm going to click a different eye, and I get different face cards, same suit but different color, or same color but different suits, and so we can explain what's going on if what? I mean, if you did this over and over and over again, which maybe some of you did. When I first looked at it, I did it a few times and thought, wow, this is pretty clever. Am I saying it out loud like he says I should? Is my microphone on? Does he have the camera on? Is he watching what I'm doing? You know, all these things. And it turns out it's just, you know, a clever trick. But again, this illustrates that you can't really predict randomness. I mean, you know, the ESP thing, well, we're actually going to do another experiment later in class about ESP, see if you guys are psychic or not. Not today, in the future. And you know, there's movies like Ghostbusters where they test those things, and with the internet and computers and everything that we have going now, there's some arguments to be made for ESP. And if you look at this thing, take it at face value, hey, my card's gone. Is he really doing what he says he was going to do? Sure, he removes your card, but he removes everybody else's card too, or every other card. So, if you don't believe in the ESP, how could the computer be doing the ESP? Surely Pickover's not sitting on the other end of the internet, watching people do this to read your mind. The other explanation is, well, there's some sort of trick going on, right? Because to get it every single time says that he knows how to remove random, or knows how to predict random things, which again is not possible. So let's see, do I have so I'm going to show you, we're going to take a break, but during the break I'm going to start a video. It's about 4 minutes long, and it will explain what you need to have in order to be able to predict randomness. Okay, so as soon as the video is over, then we'll break and we'll start back up at 11 o'clock. I'm going to have to, I don't know why it's not showing up here. So let me, come on, computer. Okay, so I put a link up here on the course web page for this as well. So, how is it possible to predict randomness? You guys see where this fits in, right? I'm not just showing you how it should have ended just to make class more entertaining. You've got to be able to travel faster than the speed of light in order to see what happened, because there's not really any way other than to go back in time or go forward in time. So if you can't do that, or somebody who is telling you they can do predict randomness, they've got to be able to have some sort of way of traveling through time. And so that's the rule of thumb. If they can travel through time, sure, you can pick my stocks. Otherwise, something's fishy going on. So we'll start back up, and things are going to get more exciting, although I'm not sure how, because we had Superman and Batman and Spider-Man. So in the videos that hopefully you guys watched, I talked about 3 different approaches to probability. One is the classical approach, one is the frequentist approach, and the other is the subjective approach. And so we're going to think about a couple of experiments that you might call. Anybody ever been to the county fair or the state fair? And you go there and you see these booths, or you go to Hershey Park or places like that, and they've got these games you can play, and you pay money, and if you win, then you get some prize, and if you lose, then you get nothing. So at the county fair, there's a game. Sometimes it looks like this. There are 3 cards, and you pay like $10 to play this. And the first card is red on both sides. The second card is red on one side and blue on the other side. And the third card is blue on both sides. Okay, so these 3 cards are randomly shuffled, and you reach into a hat and you pull one of the cards out, and you see a red side. Okay? Now, the question is, what's on the other side? Is it red or is it blue? And you have to decide. You say, you know, if you think it's red, you say red. If you think it's blue, you say blue. And if you're right, then you win the prize, like a stuffed unicorn or something. Question? No. Oh, no question. Okay, so that's the setup. That's the scenario. And so I want to know what you guys think about this. If you see a red side, what's the probability that red is on the other side? So the second side of the card is red. And here are your choices: 0, a third, a half, 2/3, 100%, or some other number. And we'll let you guys see what everybody else is thinking on this as well. All right, so make sure you get the scenario correct. You reach into the hat, you pull it out, you see a red side. You've got to tell what's on the other side to win the prize. So what's the probability? So think about this in terms of information. There's going to be some information that you gain by pulling out a card and seeing one side. And we want to use the information that we have, but just because we have some information, that doesn't mean that all uncertainty is gone away. So there's always a chance that we're going to be wrong, even if we have a complete and full understanding of the situation here. Okay, so let's see how many responses we have. Hide this, I can see 30. All right, that might be enough for now. Those of you that said a half, why did you say a half?
Because if you pull the red card, that means you either got one of the two cards. If you pulled the red, you couldn't have got the blue on both sides. So
okay.
It has a red back or it has a blue back.
Okay, so you're saying there's two choices for the back side. There's either red or blue, and then you're applying the classical approach to probability, which says those are equally likely. So 50-50, right? Whether you thought about the classical approach or not, that's what's going on. Those of you that said a third, why did you say a third? Anybody want to venture an explanation? No? Okay, what about, it looks like 3% of you that said 2/3. Why'd you say 2/3? Because it turns out you're right. The probability is actually 2/3 that the color on the back side is also red. Why is that? Oh, and now 6% of you got that right. Congratulations. Okay, so what's going on here? I'm going to use notation that says I want the probability that the second side is red given that the first side is red. Okay, right? So I reach in there, I pull out the card, I see a red side, that is R1. So this is conditional probability. There was a video on this. And conditional probability can be written as the probability of the intersection, so the probability of R2 intersect R1, divided by the probability of what we're conditioning on. All right, so the intersection would say we have the card that is red on the front, or the first side is red, and the second side is red. What's that called? That's called the red card, right? This we call the blue card, and maybe we call this the mixed card. Okay, so I have the probability of picking the red card on the top, but I know that I've seen a red side, so that means that not everything is possible. In other words, the universe that we're describing, or we're thinking about here, which says, if you think about this in terms of a Venn diagram, here's the red card, here's the mixed card, here's the blue card. I know that, what do I know? I know that this has happened. So that's now the relevant universe. So I would say, what's the probability of seeing, actually that's not quite the probability of it's not the relevant universe. We'll go more like this. And let me get rid of this part. So you can think of this in terms of a Venn diagram. But what we really need to know then is, what's the probability of red 2 intersect red 1? Well, that's just the probability of drawing the red card. And then what's the probability of drawing the red card? If I randomly choose between these three, it's a third. Okay. Now, what's the probability of the first side that I look at being red? That's a half. Why is that a half? Well, for the same reason that was argued over here. It's either blue or it's red. There's equal number of blue sides and red sides of cards, and so we get a third and a half. And so now, in order to find this probability, I'm going to take a third and divide it by a half, and that gives me 2/3. Okay, so it's very important to know what kind of information you have, first of all, and what the information's telling you. So in this case, what I've done is I pulled out a card. If it's the red card, how many ways can I see a red side? Well, there's 2 ways to see a red side. So there's two red sides. Okay, if I pull out the red and blue card, how many ways are there to see a red side? Just 1. So there's 3 possible ways to see a red side. Right? 2 from the red card, 1 from the red and blue card. And of those 3 possible ways, how many have red on the back? Well, there's 2 that have red on the back. So the probability is 2/3. Okay, so that's an interesting question. So you should think about that. There's another game that I like to play, and all sorts of other people like to play it as well, called Let's Make a Deal. Anybody ever heard of that game show back from the 70s? There's a remake of it now with Wayne Brady as the host, and they never do this particular game in the new one. At least I've not seen it where they do variations on it. But the way this works is people dress up in crazy outfits and they do crazy things, and they try and get the attention of the game show host, and he walks around this audience and he'll say something like, if you can give me a rubber band and 2 paper clips, I'll trade you that for either what's in this envelope or whatever's in my pocket. And there might be like a bunch of money in the envelope, or a key to a car in the pocket, and so people scramble around. Hey, do you have any rubber bands? Do you have any paper clips? Someone opens their purse, and they help each other out and so forth. And then they kind of make deals and trade their way up to this last scenario where they're told that behind one of these curtains or one of these doors, there's a fabulous prize like a Ferrari or a pile of money or an all-expense trip paid around the world, and a trip around the world. And behind the other 2 doors, what are there? There's donkeys. So gag prizes, unless you live in Lancaster County like I used to, the donkey's not going to really, you're not even going to want to take it home. And so you pick a door. Who wants to play this game? You want to play? All right. So you're going to pick a door. Go ahead.
Door number 1.
So you pick door number 1. And then the game show host, used to be Monty Hall, who died a few months ago, I think. He will open one of the other doors and show you. What does he show you? A donkey. Right? So you can have whatever is behind door number 1 if you choose. But just to make things interesting, he's going to open one of the other doors and show a donkey. And then he's going to say, all right, you can either stay with your initial pick, or you can switch to the other door that's unopened. So I want to ask you guys what you think is the best strategy for Let's Make a Deal. You can either switch, you can stay, or you might think it doesn't matter if I switch or stay. I could just randomly flip a coin and then decide whether I should switch or stay or not. And let's see how many. We have 17 so far. And this is a really good illustration of information. You know, what kind of information analysis you need to do in order to make the best decision. So it's what we have here is 41% of you, 39% now saying it doesn't matter if you switch or stay. Does anyone want to tell us why they said that? Go ahead.
Because no matter what, you're always going to be able to show a donkey. So it's still 50% chance. So it does not matter.
Okay, so you're saying that when he opens a door and shows a donkey, now that instead of being 3 doors, now there's only 2 doors, and so you got 50-50 chance because 1 out of 2, so classical approach to probability. Okay, anybody else say the same thing? Think anything different? Those of you that said to stay, why are you saying to stay? Maybe, okay, I'll venture a guess. Maybe you think the same sort of thing as, that, you know, it doesn't matter, it's 50-50 now, but first impressions, you know, go with your initial pick because maybe you're inspired somehow. Does that sum it up? Does anybody else have anything else to say about that? No? Okay. Those that said to switch, hang on a second. First, let's ask, what are you going to do? Are you going to switch or stay?
Switch.
You're going to switch? Well, guess what? You won. Now, you might think I just made that up, but I didn't. Really. Before I even drew the doors, I said, the money's behind door number 2. And so you switched. Why did you switch? Or go ahead. Why would you switch?
When you have your first option, you have a 33% chance of picking the right door. So chances are you have the wrong door picked when you pick originally. So them showing you a donkey and then giving you the option to switch, your chances now go up by 33% because you can now choose a door that is more likely than the first one you picked.
Okay, so what's the probability of winning if you switch?
66%.
So it's 2/3. Okay, everybody hear this? So what he said, and he's absolutely right, is when you initially pick, the chances that you're going to get a donkey are 2/3, right? Because there's 2 donkeys. And you know that Monty Hall or the game show host is never going to open a door and show you the money. He's always going to open a door with a donkey. So you hope that you pick a donkey the first time around. And the chances of doing that are 2/3. So if your strategy is to switch, 2/3 of the time you're going to pick a donkey and you're going to switch to the money. Whereas if you initially pick the money and you switch, you're going to switch to a donkey, but how often do you initially pick the money? 1/3 of the time. Okay, so we got a lot going on here, and I think it's important to first of all recognize the information that we have, and then we have to say, what's, given the information we have, let's make sure we use it correctly. Because there's all sorts of information out there, and people are making assessments of probability oftentimes incorrectly. So now it's 29% for the switch. So what's the first piece of information we have? Given the setup, we know Monty Hall is never going to open a door that has the money behind it. What's the first piece of information? Well, your initial pick. That's the first piece of information. Right? Now, given your initial pick, Monty Hall is going to open one of the other doors. Right? So the door that he opens is the second piece of information. Now, you can use what's called Bayes' theorem to write down the probability of winning given the given where the prize is. Okay, so we're going to say that M means that they open door number 3. All right, so I think M is for Monty Hall. So he's going to open door number 3, and we're going to say, what's the probability that he's going to open door number 3 given that the money is behind door number 1? Okay, so if the money's behind door number 1, what's the probability he's going to open door number 3? Well, if the money's behind door number 1, let's see. What do we got a condition on here? Yeah, so in this scenario, door number 1 was picked, right? So let's say you pick door number 1, and the money's behind door number 1. So the probability of opening door number 3 is a half, right? He's going to randomly choose between those doors. So the probability that he opens door 3 given that the money's behind door 2 is what? So you pick door number 1, the money's behind door 2, probability that he's going to open door number 3 is 100%. Okay, and we can do the same thing. What's the probability that he opens door 3 given that the money's behind door 3? So if the money's behind door 3, he's not going to open that door. That probability is 0. Okay, so we want to know then, what's the probability that the money's behind door 1 given that he opens door number 3? Okay, so this is just going to be the probability of 1 times the probability of opening door 3 given 1 divided by probability of opening door number 3. Okay, so how do we get this probability of opening door number 3? Well, this is the probability of opening door number 3 and the money behind door number 1 plus the probability of opening door 3 and the money's behind door 2 plus probability opening door 3 and the money's behind door 3. So we know this last part is 0, right? And so we can use this information here and here in order to figure out this probability here. So this is going to be equal to the probability of, so we got m given 1 times the probability of 1 plus the probability of m given 2 times the probability of 2. So we said this first one is a half. What's the probability of the money behind door number 1? That's a third. Plus probability of m2 or m given 2 is 1. And what's the probability money's behind door number 2? A third. So we get a sixth plus a third. What's a sixth plus a third? It's a half. Okay, so what we're saying here is unconditional on wherever the money's at, there's a 1/2 probability he's going to open door number 3. Doesn't matter where the money is, doesn't matter anything else. There's a 1/2 probability that he's going to open. Well, we know the money's not behind door number 3, so there's a 1/2 probability he'll open door number 3. So given that information, then we can now plug this in here, and we get 1/3 times 1 divided by 1/2, which is, do I have that right? Yeah. Sorry. 1/3 times, this should be a half. Right, so a half. My eraser, let me erase. So this is equal to a third. So that means the probability the money's behind door number 1, given that he opened door number 3, and you pick door number 1, that's included in this, is a third. And so that means, we showed it here using a probability, but what that means is the probability that you're going to win if you switch is 1 minus that, so that's the 2/3. Okay, so the best strategy is to switch. Now if you come over here to the week 3 folder, you'll see Let's Make a Deal applet. This only runs in browsers that support Java. So if you're having trouble grasping this, you're still thinking, wait, there's 2 doors, it should be 50-50. Go to this link, open it in a browser that supports Java like Internet Explorer, and you can play the game a bunch of times. So I picked door number 1, door number 2 is open, show me a donkey. I'm telling you the best thing to do is to switch. Now I switched and I didn't win, did I? No, I didn't. So I'm going to do it again. That time I switched and I won. And you can play this over and over and over again, and it's this nice little sequence of 3 clicks, and then you switch. And it's too small for you guys to see, but I'm going to play a couple more times. Alright, it says in 21 games in which I have switched, I won, that's 16? 16 times. So that's quite a bit more than a half, isn't it? Yeah, and let me play it 10 more times because it's so much fun. If you guys have ever played like Xbox or Wii or anything like that. Anybody ever do that? No? You guys just do homework all the time? This is way more fun than all those things combined. Alright, 30 games I switched, I won 22 times. How many times did I win when I didn't switch? Well, I only did it a few times. So let me play a bunch of times here real quick. Alright, so 30 times that I didn't switch, I won 11 times. You can't read that, but you'll just have to trust me. And you should go and play this on your own. And doing simulation is a good way to understand things that are difficult to understand. So what we're able to do here with probability and with thinking about things in a coherent and clear manner is to extract all the information that's available to us and use that to come up with the best strategy. And that's what we want to do with statistics. Given the data, let's extract all the information that we can and then use that to make the decisions that we need to make. But that doesn't get rid of what? The random part, the uncertainty. Just because I go through this process doesn't mean I'm going to get it right. In fact, I can measure oftentimes how much randomness or what the variability is that comes from the random part. And that's a big deal. Being able to estimate the randomness or the error or the variation in data is something that's you're going to learn how to do in this class. So, what we used here to do this calculation is something called Bayes' theorem. And Bayes' theorem basically says the probability of A given B is equal to the probability of B given A times the prior probability of A divided by probability of B. And in the interest of time, I'm not going to go through. There's a very interesting problem with going to the doctor where you go to the doctor and they say, well, we think you have some disease and maybe it's a rare disease, and then they say, let's run a test. The test comes back positive and they say, oh, you've got the disease then. And it's like cancer or something, so you have to get your arm cut off or something like that, or you're going to die in 3 months. And so you can use Bayes' theorem to analyze that probability. In other words, Bayes' theorem is all about what's called a posterior probability. So we want to know the probability of some event A given information that we call B. We've got a prior probability over here, which is just the probability of A unconditional, and then we say, okay, given B, the positive test result, for example, how does that now determine or help me calculate the probability that I actually have the disease? If it's a really rare disease, then the prior probability of the disease might be like 10% or 1% or 1 in a million, something like that. You get a positive test result, how does that affect the probability? So I'm not going to go into that because we're running a little bit short on time, and we need to talk about some other things, including counting methods. So whenever we do probability, we have to determine which approach we're going to use, and one's called the classical approach, again, where you count the number of possible outcomes and say they're all equally likely. There's the frequentist approach, which is what we would do with we did the simulation over here. Let's make a deal. It says let's just run the experiment over and over and over and over again count the number of times we have a success, count the number of times we have a failure, and then there's the subjective approach, which says, well, the classical and the frequentist approach, those aren't always the best thing to use. Like, for example, the Super Bowl. When was the last time the Eagles played the Pats in the Super Bowl? 2004, 2005, whenever that was. Who won? The Patriots. So do we have... I mean, we could assess the probability that the Eagles are going to win based on the classical approach, which says there's two teams, there's two possible outcomes, and so we'll say it's 50%, 1 out of 2. That's one way we could do it. We could use the frequentist approach, which says, let's just look at what's happened in the past, the number of times that they played, who's won the most, and so forth. But that doesn't really work in this scenario. Why? Did they play during the regular season this year? No? Okay. So different teams than when they played the last time. But even if they had played this year, the quarterback for the Eagles is hurt and is backup playing. So all sorts of things, all sorts of variables are changing all the time. So the frequentist approach doesn't really work there as well. But lots of people are going to be betting on this, right? Maybe you're with your friends, you think the Eagles are going to win, they think the Pats are going to win, so you have arguments about it, and finally you say, okay, put your money where your mouth is. If you really think they're going to win, then let's have a bet. And that's what we call the subjective approach to probability. You can't write down objectively everything that goes into why you think the probability is whatever you think it is that the Eagles are going to win or lose, but based on your subjective, your feelings, you can come up with a probability. Counting then is a very important part of doing the first two types of probability, and those probabilities can be used to help inform subjective probabilities. So counting is really important, and there's something called the product rule. That says if I've got multiple tasks to complete and I want to know the total number of ways that I can complete the process that's made up of these tasks, all I have to do is multiply the numbers together. So, for example, you guys are hanging out Friday night and you say, let's go get some food somewhere, and you say, okay, let's go to this restaurant, fast food or whatever, and you say, how many different main dishes can I get from this restaurant? Now, let's just say it's a sandwich shop. So there's 10 different sandwiches you can get. And this is not, of course, including all the varieties of ways in which you can get the sandwiches, with mayonnaise, with mustard, with pickles, lettuce, all that stuff. Just say there's 10 sandwiches, and say, okay, so I got my main dish. What about a side order? I want coleslaw or mac and cheese or French fries or whatever it is. Say there's another 10 ways that you can do that. And then what else do you get when you go out? A drink. Maybe there's 7 ways to get a drink. 7 different beverages. So this is not including small, medium, large, but all that could be added in. The numbers would go up significantly. And then finally, what do you have? Dessert, right? Main dish, a side, drink, and dessert. And let's say they have 4 different desserts that night. So how many different ways can you order from this restaurant? Well, the product rule says just multiply all those together and you get, what is that? 2,800? 2,800? Okay, how much time do you need to decide? I mean, if you're going to look at all the combinations, I don't know why they call it fast food and they offer so many different choices. And you're sitting there and people are like, hurry up. Like, well, there's like 56,000 different ways I can order. Give me a second. I mean, this is a small example, right? So again, if you're with your sandwich, you could say, are there, 8 different toppings you could put on the sandwich? So there's 2 to the 8 different ways you could do that. So 256. So multiply that by 10, and that's the number of ways you can pick a sandwich. And then multiply all that in. So these numbers get very big very quickly. Special cases of the product rule are what we call, or there's 2 of them called permutations and combinations. And permutations actually are not all that different from combinations. What we're really doing is saying, let's take, say, everyone in the class. Let's say there's only 7 people in the class right now. And we want to break them up into 2 different groups. How many ways can we do that? Well, we have 7 choices for the first person. 6, 5, 4, 3, 2, and 1. And so we're breaking them up into 2 groups, but we're saying we're only going to pick one of the groups. And order matters. Sorry, I have to write with my finger, doesn't look that good. Okay, so in other words, we've got 7 people in the class and we want to pick a class presidency. So if we have the president, the vice president, and the secretary, and it's Jeff, Bill, and Samantha, that's a different presidency than if we have Samantha as the president, Bill is the vice president, and Jeff is the secretary. Okay, so that's when we would use permutation. So we have 7 factorial ways. That's 7 factorial. Let me write that someplace else. Seven factorial ways that we can do this, but we don't care about the order of the 4 people that aren't in the presidency. So we're going to divide by the number of ways that we can reorder the 4 people that are not chosen for the presidency. So if we only care about the order of the 3 that we pick, then this number is going to be 7 factorial divided by 4 factorial. Now combinations are similar, except for order doesn't matter for either of the groups. So with combinations, we'd say we have 7 factorial ways that we can arrange everybody. We don't care about the order of the 4 people that are not selected, and we also don't care about the order of the 3 people that are selected. So think of it as a committee. If we want to make a committee of size 3, we have Jeff, Bill, and Samantha, or Samantha, Bill, and Jeff, or Jeff, Samantha, Bill. Doesn't matter what order, it's the same committee. So combinations are going to be quite a bit less than permutations. So at this point, I'd like to ask you guys another question. And we got about 10 minutes left, but that's not the question. So what do you think the probability is that at least 2 people in this room have the same birthday? Okay, so I want you to not try and calculate this because we're running short on time. I just want you to think. I think there's probably 35, let's say there's 35 people in the classroom. Of 35 people, what's the probability that at least 2 of us have the same birthday? And then I'm going to ask you to put your birthday in. I'm going to offer you a bet for an A in the class. You can be done with this class in week 3 if you want. Either way. I'll explain the bet in a minute. So we got 7 results so far. So again, we got 35 people. What's the probability at least 2 of us have the same birthday? And again, you should be thinking probability is about using the information that we have in the most efficient way, but then there's always still going to be some sort of uncertainty. So what information we have, we know there's 35 people in the room, and we don't care about the year, we're talking just day of the year. So I'm probably the oldest one in here, but it's possible that I have the same birthday as somebody else. All right, so we got 22 results. That's going to have to be good enough for now, but the next question I will ask, everybody needs to respond. All right, so that's a really small number, pretty small. 7%, 9.3%, 10%, and then we've got 75%, 10%, 2 out of 35. So I see quite a few low numbers, like 9%, 7%, 5%. So now I'm going to give you an opportunity to make me a bet, and here's how the bet goes. If at least 2 people in the room have the same birthday, then I win the bet. If there's not 2 people with the same birthday, then you win the bet. So if you want to take that bet, you can. If you're right, then you never have to come to class again. You get an A in the class, no questions asked. You can tell all your friends you got an A in the class in week 3. You're that smart, and it will be, you know, a boon to you. If I'm right and you lose the bet, almost exactly the same thing happens. You don't have to come to class anymore, but instead of an A, you get an F.
Don't you have our information?
No, I don't. That's the register. The registrar's got that. I don't have access to that. I never did ask you your birthday yet, but I'm going to ask you that now. So, oh, before I ask you, all right, while I'm asking you, who wants to take that bet? So put your birthday in. Just say three letters. So April 3rd would be APR 03. Anyone want to take that bet? One taker? 2? 3? Sure, about 4? 5? Whoa. Okay, but I'm going to count. Everybody's got to answer because we're going to make sure this is done right. 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. 33, 36, 39, 42. All right, there's 45 people here. So I need 44, and I'll just tell you what my birthday is after. Did you have your hand up?
Yeah, I want to take the bet.
Oh, you want to take the bet? Okay.
Do we do it in a year?
Nope, just the day. So that's 33, 35, 36. I mean, those of you that said like 0.000001, that's your chances of winning the lottery are hundreds of times bigger than that. So you should be taking this bet. All right, we got 41, and I will tell you my birthday before I pull up the results, just so you don't think I'm faking this. Okay, 41, is that all we're getting? Anybody else? 42. All right, there's 43, so there's just one person, unless somebody put in multiple responses. All right, my birthday is August 27th, by the way. Oh, so close. All right, so 6-3, that means June 6th, so just keep that in mind. Let's see, what else have we got here? August 16th, raise your hands. 1, Did you put it in twice?
Yeah.
Oh, yeah, sorry. Yeah. So did you guys know beforehand that you had the same birthday? Is that amazing? No, wait, now tell me again who took the bet. This is your chance to say you didn't take the bet. Honestly, what else have we got here? I'm sure there's going to be more. June 3rd? Where's June 3rd? June 3rd, raise your hand. Is there only one June 3rd? Someone said June 3rd. Okay, not June 3rd. March 6th. Oh man, we just had one pair? Usually there's like 5 or 6. Okay, so what's going on here? Why is it so big? Or rather, why would I think the probability is really high, so I'm of course going to make crazy bets like that. Well, if you come over here, you can look on this birthday problem generator, and you can look at birthdays, and you can say, if we have 45 people in the room, which is right here, what's the actual probability? 94%. So that's almost like, you know, shooting fish in a barrel or something. 94% chance that I was going to win that bet. 5% chance you're going to win that bet. You can mess around with this, put it down to 23, and see that when 23 people are in the room, the probability is almost 51%. So the next time you're in a big group, you can ask them, hey, what do you think the probability is at least 2 of us have the same birthday? And they'll all say 2%, 3%. You say, okay, let's make a bet. And you can ask them all their birthday. So this is kind of a cool applet. You can actually click on the sample button, and it will generate birthdays for whatever size you've done, and you should go and look at that. But this probability comes from permutations. So if you want to know how to calculate the probability, all you have to do is say, what's the probability, or what's the number of ways that 45 people can have a unique set of birthdays. In other words, there's no shared birthdays. And that turns out to be a permutation. It's 365 factorial divided by 365 minus 46 factorial. So we'll see you guys next week. We talk about chapter 6, and then following week will be chapter 7, and then the following week will be the midterm exam. Again, we're going to use Excel on the midterm exam, so we'll see you guys then.